Right, in the last section, the previous video, we learned that arithmetic sequences behave like linear functions and that geometric sequences behave like exponential functions. Today, we're going to look closer at that relationship and the connections that they have. And so we built a chart here for you guys to compare. We'll start with the arithmetic sequences and linear functions. So when we're talking about arithmetic sequences, these are the two formulas that we're going to use. With a sub 0 plus our common difference, remember that's what d is the common difference, and our term number. Or you can do the a sub n equals a sub k, that's any term, plus the common difference multiplied times the term number minus the term number for k there. You can compare those in the linear functions when you talked about the slope-intercept form, which was mx plus b. These are very similar to each other. For the point slope formula, that was when we had the y1 plus m times x minus x1. These two formulas are very similar to each other. Now remember, with sequences, we're only putting in whole numbers, so it is not continuous. You are not connecting those dots, where with linear functions, you can put anything into x and have our decimal values. Now, with geometric sequences and exponential functions, you do have similarities in those equations as well. Here are the two that we're going to use for geometric sequences. This one right here is when we're starting with that term at 0. This one, we can do that any given term. That's the big difference between these two right here. So you have the n minus our term number, whichever term number you're using the term of. For your exponential functions, then you see that a times b to the x power, or a times r to the x power, for that initial one, and that's when we're putting that initial amount as a. The other one here, you've got y sub 1 times r times x minus x1, which is very similar as well. We're going to talk about these changes in linear and exponential functions as we move through this unit a little bit further. So let's talk about linear versus exponential here. With a linear function, we're looking at this equation here. With an exponential, you're looking at the a times b to the x power. In a linear function, over equal length input intervals, the output values change at a constant rate. That's what you're looking for, is that constant rate, that constant common difference. For an exponential, you're looking over equal length input value intervals. The output values change proportionally. So you're looking for that common multiplier there, or common ratio. The change in m in y is based on addition with linear equations, where here it's based on multiplication. So if our common difference is addition or subtraction, that's where you're going to see this. And then if it's a multiplier, that's where you're going to see an exponential function. If you have 2 points, you can write the equation of a linear function, an exponential function, an arithmetic sequence, or a geometric sequence. So given 2 points, you can write it in any of those forms. All right. So the first thing we're going to look at here is with Mr. Passwaters gave us some examples so that we can work through these. It says selected values of several functions are given in the table below. For each table, determine if the function can be linear, exponential, or neither, and give your reason. So looking at this first table, we have those equal value intervals there. And so I'm going to check my differences here. And so this went down by 2, down by 2, down by 2 each time. And so this would be considered a linear function. And the reason for that is over equal length input value intervals. All right, over equal length input value intervals, sorry. The output values change at a constant rate. And so that's how we know it's linear. It's changing by that constant rate here of -2. And so remember when we were writing equations, that tells me that common difference, the d value is -2. Sorry, that is not the case because these are not by an input value of 1. Sorry about that. All right, so for this next one, we're looking at the values. And so this goes up 1, this goes up 3, this goes up 5, and this goes up 7. So in this case, we do not have a constant rate. We do not have a common multiplier. So if I divided each one of these, I wouldn't find a common number. So this is neither. And that is because over equal length input values, value intervals, output values don't change at a constant rate or proportionally. So constant rate, so we know it's not linear. Proportional, we know it's not exponential. All right, so when we look at this next table here, I can go ahead and see that this from 1 to 2, we multiply times 2, we multiply times 2 on each one of these cases. So this was a times 2, times 2, times 2, and times 2. So we have that proportionality, the common ratio is being multiplied times 2 there. And so we know this is exponential. So over equal length input value intervals, the output values change proportionally. So we've got that common multiplier there, so we know it's exponential. As we look at that next chart, that's going to be the same case. From here, it went from 80 to 40 to 20 to 10 to 5. So we know this was multiplied times 1/2, 1/2, 1/2, 1/2. So we have that common ratio there that we need. All right, here is a word problem in that type of equation. And this type, it says, a wild rumor is spreading that Mr. Passwater won 3rd place in the world's strongest man contest. The number of people that have heard the rumor can be modeled using a geometric sequence. So when we see that geometric, we want to think that's exponential. That's the one with the common ratio. Where the 43 people had heard the rumor on day 3, and 140 people have heard the rumor on day 6. According to the model, how many people to the nearest whole number have heard the rumor by day 10? And so last time we did this, now we're just putting it into a word problem sense. And so we are given here that on there were 43 people that heard the rumor on day 3 and 140 people that heard the rumor on day 6. So they've given us 2 different points. 140 is the last one. So actually, I'm going to go ahead and write that equation here so that you have it again. All right, we said G sub n is equal to G sub k So I'm going to plug in the 140 for my G sub n, and then 43 right here for my G sub k. I don't know the rate. And this was day 6 and day 3. So that's going to be 6 minus 3. All right, so now we're ready to divide by 43. And so we learned last time that to get rid of this 3 right here, you take the cube root. And so I can write that as well as 140 over 43 to the 1/3 power would be equal to my r, since we can't take the actual cube root of that because it's going to give us an ugly decimal we don't want to mess with. Now we are looking for the 10th day, so now that I have my equation, which I'll go ahead and write again. All right, so there is my equation written in general forms. I kept the 43, and then this is any term I'm going to find with the 140 over 43 to the 1/3 power as my rate. All right, so we're looking for day 10. And so all I need to do is plug in the 10 for my n. And this would be calculator active. So we go ahead and we plug that into the calculator. All right, so I put it in my calculator so that you can see I can put it exactly the way it shows on my paper here. I did use the alpha y equals to get the fraction bars so that it looks just like it does on my paper. And so there we go with 675.576 if you were. When we round, remember we're rounding to 3 decimal places or truncating either way. And so there is our value. And so we can say approximately 676 people have heard the rumor. All right, for our last one here, it says a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. If the 5th row has 31 seats and the 11th row has 49 seats, determine how many seats there are in the 25th row. And so again, last time I talked to you, you can get that common difference a couple of different ways. You can use the formula backwards to solve it, or we can find our difference in our y's over the difference in our x's, since we've done that quite a bit in this course. I'll go ahead and do that. So that's 49 minus 31 over 11 minus 5. And so we get the common difference is 3. So now to write our equation, we can pick any of the values that are given. And so I'm going to go ahead and go with the 31 plus 3 is my common difference. Actually, let me go ahead and write that equation there so that you guys have the formula listed one more time. The more times you write it, the better you're going to get at it. And so there is our formula. Now we can plug in the parts that we wanted. So we're going to plug in 31 for our a sub k and 3 for our common difference. And then we have that n minus 5. And now we can simplify. And so we've simplified our equation. Our last step is to find how many seats there are in the 25th row, because that's what answers my question that's being asked here. And so I want to use the formula that I just wrote to find that out. And so we get 3 times 25 plus 16. I'm putting the 25 in the place of n to find that term. This is my term number, and I'm trying to find the term. And so that's going to give me 75 plus 16. And so my 25th row has 91 seats. There we go.